For decades, people have been trying to predict the market, right? The smartest minds in finance have thrown everything they have at it. But what if we've all been looking in the wrong place? What if the key isn't a smarter person, but a totally different kind of intelligence? Today, we're diving into this wild world of financial machine learning to ask, are these new algorithms finally cracking the code?
Okay, so let's just get right to it. The big question right up top. Can machines actually predict the market? It sounds like a simple yes or no, but the answer is, well, it's a lot more complicated than that. And to even get close to an answer, we first have to really wrap our heads around why this is such an incredibly difficult problem to solve in the first place. So, before we can even talk about these new machine predictors, we need to understand the puzzle they're built to solve. You see, trying to predict the market isn't like trying to predict the weather. The weather doesn't change because you forecasted it. The market, well, the market is a whole different beast. It's almost like it's actively trying to stop you from figuring it out. And here is the absolute key to understanding why. A stock's price is not just some random number. According to modern financial theory, that price is already a prediction. It's the collective wisdom, and yeah, sometimes the collective panic, of the entire market, all crunching every piece of available information to make its best guess about the future. So you're not just trying to predict a value, you're trying to out-predict a massive prediction engine made of millions of other people. This whole mess really boils down to three huge challenges. First, like we just said, prices are already predictions, so you're joining a game that's already in progress. Second, the amount of data is just insane. We're not talking about a few variables. Researchers have found hundreds of potential predictors for every single stock. But the third one, that's the real kicker. Even if you had all that information, we don't actually know the rules of the game. The true formula that connects all that data to the price, it's a complete mystery. So, to tackle this incredible puzzle, two very different ways of thinking have emerged. You can really think of it as a battle between two scientific cultures. The established old guard, which is traditional econometrics, versus this disruptive, powerful new challenger, machine learning. The old guard, traditional econometrics, it's all guided by economic theory. Its core belief is something called parsimony, which is just a fancy way of saying simpler is better. The main goal is to test a specific hypothesis, but then machine learning comes along and throws that playbook right out the window. It's guided by one thing and one thing only, pure predictive power. It loves complexity, and its only goal is to be accurate, no matter how complicated the model gets. And this clash of philosophies, it leads to a discovery that is truly mind-blowing. And this brings us to a huge turning point in our story. For decades, one single belief was basically sacred in the world of statistics. But machine learning didn't just question it, it completely blew it to pieces. This is that sacred belief. It's called the principle of parsimony. It's been the bedrock of this field for over 50 years. The whole idea is that you want the cleanest, leanest, simplest model possible. Why? To avoid a little trap called overfitting. That's when your model gets so complex, it stops finding the real pattern, the signal, and just starts memorizing all the random junk in your data, the noise. But here's the twist. What if that golden rule, the one everyone has been following for half a century, was actually holding us back? Because it turns out the exact opposite can be true. The latest research is showing that in finance, the models with an absolutely astronomical number of parameters, we're talking way more settings to tweak than actual data points, can actually be the best predictors when you test them on something new. This just completely turns conventional wisdom on its head. And this chart illustrates this bizarre phenomenon, sometimes called double ascent, perfectly. So, look, you start with a simple model, and its performance is, it's okay. Then, as you start adding complexity, performance actually gets worse. That's the classic overfitting the textbooks warn you about. But then, and this is the amazing part, if you just keep going, if you push the complexity to extreme levels, something wild happens. The performance doesn't just recover, it shoots back up, often even higher than the simple model to begin with. This super high complexity zone has a name. It's called over-parameterization. Imagine you're trying to build a house, but you have more tools in your toolbox than there are bricks in the whole building. It just sounds like it shouldn't work. On paper, it looks like a complete recipe for disaster. So why doesn't this just completely fail? Well, the intuition is that when you give the models so many possible ways to find a solution, it can find one that's not just accurate, but also really smooth and stable. It's like having a soundboard with a million tiny little sliders instead of just a few big, clumsy knobs. It can make all these tiny adjustments, and this basically act as a form of self-regulation, making the whole model much more stable in the end. So this new philosophy of bigger is better obviously requires a whole new set of tools. Let's just do a quick flyby of the main methods that researchers in this space are using now. All right, the toolkit is pretty fascinating. First, you've got things called penalized models. Think of these like a strict manager that automatically benches any predictors that aren't pulling their weight. Then you have dimension reduction. This is all about taking that huge, messy pile of data and condensing it into just a few clean, powerful supersignals. Next up, decision trees. These work kind of like a game of 20 questions, asking a series of simple yes-no questions to uncover really complex relationships. And finally, you've got the heavy hitters, neural networks. These are basically universal approximators that can learn almost any complex, nonlinear pattern you can throw at them. So what does all this mean for the big picture? I mean, this is about more than just building a better forecasting tool. This is actually about a fundamental shift in how we see and understand the economy itself. So let's just pull it all together. What are the big takeaways? Well, for one, researchers can finally analyze data on the same massive scale that the market itself does. That's a game changer. Two, that old cautious rule of keep it simple is being completely upended by the surprising power of go big or go home. And this really changes the mission. The goal is no longer just to test old theories, but to draw brand new, high-definition maps of the financial world as it actually is. Think of it like this. The old way was you start with the theory, and then you go look for data to prove it. This new culture completely flips that on its head. It uses machines to find interesting, unexplained patterns in the data first. And those new discoveries, they become the inspiration for the next generation of economic theories. It's almost like doing science in reverse. And all this brings us to one final provocative thought to leave you with. We've seen that these machines are getting incredibly good at finding patterns in the market. But what happens to those patterns when everyone starts using the same hyper-effective machine to find them? Does the edge just vanish into thin air? Or does it create a whole new kind of game entirely? That's a question for the future.